All right. So I had a couple of good questions at the break. I want to clarify, and I hope I can remember them. So the first one is, does any of this apply in a single-threaded process? The answer is, absolutely it applies in a single-threaded process because you can be servicing more than one client concurrently with a single processor. It's called time multiplexing. And that's what we're talking about. When you have any kind of server and multiple clients and have only a single processor, that's exactly what we're talking about. So forget about multi-threading. This talk is not about multi-threading. There's one benchmark that talks about multi-threading, and it's not the point of the talk. It is about single-threaded applications that service more than one thing concurrently, meaning time-sliced. Okay? The second point is, the less locality you have, the greater the cache miss, the slower the program runs. So you can have less locality by having more interruptions when you're focused on your block of memory that you're trying to get locality for, and you can have lower locality because your block of memory is bigger, and therefore it's hitting the memory, but it's all over creation, and so that's not fitting in a cache. So even though it's hitting the block of memory, your locality is going down. It can go down because of inconsistent, focused hits of instructions, and it can happen because of a larger block of memory that's much bigger than your cache size. Does that make sense? Great questions. Just wanted to clarify that. All right. I plan to finish this talk. I'm a little bit behind, but it's okay because we're at a good stop. We were at a good stopping point. I'm going to finish the talk. If at exactly the hour I'm not quite done and you guys want to get up, just do so quietly, but I do want to finish the talk for the purposes of the audience. It's not going to go over by much, but it might go over a skosh because the second benchmark is mind-bending. The first one's not. So let's look at the benchmarks. We wanted to explore these dimensions and we wanted to come up with some experiments, and I got to tell you, we tried to come up with a benchmark and vary the 5 dimensions. We couldn't do it. We just simply couldn't come up with such a thing, so we settled on 4 separate benchmarks. We did not assume that we knew what we were talking about. We tried to cover a huge field, a huge space of inputs and let the cards fall where they may. So we did not have an agenda when we went into this. I promise. Just saying. And in fact, I insisted on that because there is a little small academic part of me that says we might as well tell people the truth. We use successive powers of 2. I don't know. It's somehow, I don't know. Went to a lot of courses in school for literally 20 years after high school I was in school. So I got this baked into me. You don't cheat on tests. That really bugs me. Anyway, we use successive powers of 2. So we looked at things like 1, 2, 4, 8, 16, 32, up to some big number. We looked at a very wide spectrum of things. And we traded other things off as well. So what we would do is we would say, we'll make the number of subsystems twice as many, but we'll cut them in half, so they'll be half as large. So we would have some sort of comparison to see what kinds of effects happen for problems of the same size, if you will. So that's what I'm talking about here. So take a look at this, because we're going to see this in benchmark 2 quite a bit. We're also going to see in benchmark 1, in fact, we're going to see it in all the benchmarks, that what we're doing is we're looking at trading like things, like number of iterations for number of different locations. So we'll beat on a subsystem of 1K times, and then we'll beat on a subsystem of 2K 512 times, and 4K 256 times. And it'll be the same number of instructions, but a little bit different. Kevlin, you missed all the background. Now you just have to deal with the data. What are you going to do?
I'm good with this.
Yeah, good. All right.
Right?
I'm honored that Kevlin is in the audience now. He can see these benchmarks. I've wanted him to see it for a long time. So anyway, we used this processor. We tried this on a lot of different things, and we had to pick something. We tried it with different hardware. We tried it with different operating systems. We tried it with different compilers. We picked something that's representative. We did not cherry pick anything. So you're looking at a set of data from an architecture, but there's nothing special about this architecture except for one thing. And I don't know which one, I mean, this is it, but I just want to say GCC was ahead of the game when it came to devirtualizing virtual functions over Clang. That's the one thing we noticed. And as I said earlier, now that it's part of C++ 17, I can guarantee you that Chandler will not rest until he catches up and then blows it away. So I'm very comfortable in saying to you that this is going to happen. All right. So I'm putting this up just for reference. The final benchmark is really there just because it's a line item to say, yeah, we looked at concurrency. Remember, this is not about concurrency. This is about a single processor, single-threaded program that addresses more than one issue pseudo-concurrently through time slicing in every case. Okay. Now, we tried these guys. Now, remember, these guys are particularly good for concurrency. But as far as being better for the kinds of things we're doing in benchmarks 1 through 3, they are not better than what comes with the platform. We tried them, and they don't do any better than new and delete. But we did try them. So what we're saying is, this isn't the answer. This is not the panacea for single-threaded, single-processor systems. And again, as I promise you, if you know what you're doing, these are just programs. We're people. We can design systems, and people who are really good at designing systems and taking advantage of local memory allocators can absolutely destroy the performance of these. And in fact, we made our benchmarks as friendly to these as we possibly could, and yet, you know. So, just want to make this clear. So here are our 4 benchmarks that we're going to look at. And I just have to ask, what time do I have to stop supposedly?
17:15.
Got it. All right, we'll try. So here's the first one. Whatever 15, it's a 15. I just wanted to make sure. So what we're going to talk about now is something that we build it up, we use it, and we get rid of it. Now that's a very important class of programs. And that's something I didn't expect to be particularly impressive. Because these are not time multiplex programs. These are programs that are just one person doing one thing with no time multiplexing, with no nothing, just a one user system. So I didn't expect much. Where I expected it is benchmark 2. But benchmark 1, not so much. Now it turns out benchmark 1 is a lot like a front end for a GUI when somebody's interacting with something. The front end one is really a lot like this, it turns out. It just turns out at Bloomberg that's the closest. Because you're building something up, you're doing something, and you're getting rid of it. So that's what this is. So what are the considerations? Initially, we want to investigate allocation density. Remember density, and for Kevlin's benefit, we have this acronym called DivLuck. And the first one is D for allocation density. So we wanted to measure density, and we looked at a bunch of common data structures, int, string, vector, and unordered set. Has anybody ever used any of these? Are they relevant to your programming at all? I didn't pick them because they were obscure. Okay. We didn't want locality to dominate our results, so we went out of our way to avoid accessing them. We just allocate and deallocate. The reason for that is to give this a chance, because if we were to start letting memory access matter, then all of these results would go away. We don't want that to happen. We want to look at allocation density in isolation. Then we threw in string because we said, well, you know what? Let's try to catch both of these together. And so string, we'll make them large enough so that they don't take advantage of the small string optimization. And we'll get both of them. So we're hitting density and variation of size at the same time. Okay. So here are our sample data structures. We have DS1, DS2, DS3, and DS4. Turns out we're going to have 12. But these are the first 4. So what does a vector look like? Vector of string, unordered set, and unordered set of string. So you get the idea, there's some pieces. What's interesting about these is some of them are kind of monolithic, like a vector of int. It's just one chunk. And then a vector of string, a little more. And this one has a lot of little moving pieces in it. So there are more pieces. When there are more pieces, there's more opportunity for things to spread out in memory. Intuitively, right? If you allocate one thing, it's one thing. If you allocate something and then allocate some more things and whatever, they can spread out. So the plan is for each data structure of this thoughtfully chosen set, we're going to create a new data structure, access it likely, destroy it, and repeat. We chose the overall size to be n equals 2 to the 27th. The container sizes to vary from 2 to the 8th to 2 to the 16th, which means the number of repetitions will be decreased accordingly so that the amount of work we do in each experiment is the same as I explained earlier. We want to compare like things. Okay? So here's an example. The container size is 2 to the 8th. Then the experimental repetitions is 2 to the 19th. Remember, we really are using exponents most of the time here. All right? Any questions on this? Does this make sense? Yes?
Couldn't you turn off the cache of the CPU? Oh, okay, yeah.
Okay, I could also unplug the machine. The question was, could I turn off the cache of the CPU? Yes, I guess I could somehow, maybe if I went in with a screwdriver. What's the point of doing that?
Well, you mentioned that you want to rule out the locality, so...
Ah, interesting. I wanted to minimize it. I don't know that I wanted to alter my experiment to the point where I'm doing something on a different piece of hardware. That seems like it would be unfair. I could do that in addition, but I wouldn't do that instead of this, because what I'm doing is I have a computer, and I'm trying to look at a real thing on a real computer, not a, well, I shouldn't say real thing. I want to look at a focused thing on a real computer, not a focused thing on a castrated computer. Do you see what I'm saying? It's a little too much. I couldn't think of a better word, I'm sorry. That's just the word that came to mind. I tried. But I think you get the idea. But thanks for asking. This is in runtime. So here's a vector of int. Now, you may think this is not the best presentation. I was bragging before that I'm actually good at PowerPoint, better maybe than allocators. So I looked at this and I said, you know what? That's going to be really hard for people to grok. Because here I have these 14 allocation strategies, and I've got these different sizes, and I've got these floating point numbers, and even though they're only 2 digits, it's still a little blurring, eyes glaze over, right? So we need to do a little bit better. So maybe this helps. Each result represents absolute runtime in seconds. Nah, it's not going to do it. How about this? I'll put some heading on it so you can sort of see that we have global monotonic, multipool, and multi-pool of mono, which is the combination of the two. And now you see each pair of columns is virtual, non-virtual, and then in the case of the local allocators, which are AS3 through AS14, we have the option to wink, and they're close together. You say, it's still hard to read, so I decided maybe putting some extra lines in it would help. Is it getting better? Do you see there's like a possibility? If you had this in front of you in a magnifying glass, it would help, right? So what happened when Dorothy actually landed in Oz? What happened? What did she see? Does anybody remember the movie? Something happened. She saw color. And all of a sudden you say, okay, I get it. Okay, but what about the data? Wouldn't it be nice if the data went to Oz as well? So here's a heat map. So I think that this pretty much says green is good, yellow's meh, red not so good. Okay, Kevin, that's red. These are all yellow and orange. This is green, 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 and these are all yellowish.
Yeah, if you could get rid of the color, I can see the numbers.
I do apologize. It works for some. You know, I can't win. All right. I really can't win. All right. Anyway, so I want you to look at this. The point of this slide is not what it shows, but just giving you a feel for how we're going to show it, because this is a vector, and we explicitly allocated one thing, a vector of int. So whatever this shows you, don't put too much stock in it.
Aren't the winking allocators doing strictly less work than their non-winking partners, and why do they take more time?
So you're asking a question. The question is, why is it that this is taking less time, more time than this is, even though they're doing less work?
Yeah.
Are they doing less work? How many allocations are happening in this experiment? 1. All of the work is something else. So this is not useful data. This is noise. So anything that you see here, I wouldn't bet at all. It is interesting that the global allocators seem to be a little bit more expensive than the rest, but I would not put any stock in that. We need to see some more examples first before we start, right? So let's look at benchmark 2. This is benchmark 2. And now we actually have something to look at because we have a lot of pieces together. Now it's worth taking a look at this. So take a look. What do you see? Well, we see the monotonic is doing pretty good. We're seeing multiple is doing better, but not as good as the monotonic. And we see that the combination is almost as good as just this. Now, this is just data. Who knows why it's happening? It's just data. One thing we do notice is that the global allocators aren't doing so good. And we really don't know why, because there's no way to explain it other than, well, maybe these are general purpose allocators doing a lot more stuff than they need to do. And these aren't. And less code runs faster. Remember what I said about the special implementations? They're no better than what come on GCC. Now, 10 years ago or 15 years ago, that wasn't the case. And then somebody woke up one morning and said, wait a minute, those guys are beating us. That can't happen. So they stole that implementation and put it in. Who knew? All right. So look at this. This is just a fact. I don't have to explain it. It is. Let's look at the next one. Unordered set. What do you see? Well, now this is a node-based container, and that winking, what's happening here? Oh, look at this. Look at this. There's some differences. Now, the virtual here looks like it's costing us something, but then the winking is giving it back to us in this case. So monotonic still looks like it's winning. Multi-pool, little bit worse. Notice the colors. And multi-pool of mono, right? So what do you see consistently here? Seems like monotonic is pretty good and global is pretty bad. Let's look at the fourth one. Now here are a lot of moving pieces. Okay. So what do you see? Good? Not as good? Pretty good? Ew. All right. So do you have any questions? It's just data. Okay. So now let's look at these data structures. What I wanted to do is make it a little more interesting, so I did a vector of each of those and an unordered set of each of those, just for fun. Question?
I have a short question. I was breaking my neck before.
Next.
So,
No, it's share the microphone.
Actually, not you, but he's
oh, sorry.
No, go ahead. You do first, and then you do next. Don't worry about it.
Just a short question. The strings, are they the data of the string? Is that in the?
Okay, to answer your question, all of the string sizes are 33 to 1,000 distributed evenly, uniformly, so that the short string optimization never takes effect.
Yeah, but that data is on the heap. It's not in the arena allocator.
Okay. The data is on the heap in the arena allocator.
Hi, I just had a really short understanding question. On the left column, was it the sample size or the iteration size?
On the left column. Well, we're going to get to dataset 5, so can I answer the question on dataset 5? So you understand what these are. So here's the composite data structures. What we did is we picked a fixed size of the inner ones. I'm just going to sort of show you this so you can get the idea. But basically, we're holding the inside constant, and then we're going to vary the outside with the number of iterations. So again, we have something like this. We're doing the log. Here's an example, all of these. So here, let's look at this one. So what's this? This is time. All of this is time. This is an absolute time. They're relative. They're scaled relatively. You understand what I'm saying? But there's no iterations. These are, these. I'm sorry, these. This is the size of the outermost container. The iterations times the size is a constant, 2 to the 27th. But remember now, the inner element is big because it itself is an aggregate. Okay? So now we're looking here at vector of int. Now we got a lot of pieces. I mean, there are really a lot of pieces here. This is a much bigger data structure. Not a little one, but a much bigger one. Now look what happens. These numbers are not at all comparable. When you have a larger data structure, what happens? The cache is smaller relative to the larger data structure, right? Just take a look at this. See, the winking starts to matter. It's significant. These things are worth staring at, right? It's worth looking at this stuff. If you go to the next one, notice the virtual overhead. You see this? In the winked version here, and if you look at the virtual one here, the virtual function actually is faster than the other one. How do you explain that? It's what?
It's less code.
It's less code.
It gets deduplicated.
What I want you to look at, this is quite dramatic. And if you just keep your mind on just the general idea of monotonic versus global, I mean, do I really have to talk? Or can you just look at the numbers and be happy? So if I keep going, you might see a pattern. Multipool isn't so good here. What's happening here? Notice that at some point it becomes a pass-through. When the size of the amount that I'm allocating gets too big, it passes through. That's what's happening here. You get this pass-through effect, so it's really not so good. But if you notice the monotonic, because we're building this thing up once, it's got a high utilization, but that's fine because we're using it all at once, and that's fine. When you have a high utilization, monotonic is your friend. When you have a low utilization, monotonic can kill you. Okay. Unordered set of int. And finally, unordered set of string. All right. So global allocators are always inferior. Which local allocator strategy is best? Answer, monotonic. Why? Because it's true because we're allocating all the memory at once, we're using it, we're getting rid of it. Therefore, why would we pay at all for deleting it individually? There's no reason. Don't do it. So, now we're going to grade this out. We're going to look at the relative benefits of these guys. And I'm just going to click through it quickly. And I want you to understand that this is where we're trying to look at which local allocator is best and by how much. So if you look at the multipool, this is a poor choice for this particular type. Either use the monotonic or the multipool of monotonic. And I think I said this backwards last time. I want to make sure I clarified this. The monotonic one is in the front. No, the multipool is in the front, and the monotonic one is backing it up. If you did it the other way, it would be silly. So I just want to make sure I said that right, okay? So it's multipool of mono, and you see what's going on here. And just the multipool alone is a bad choice. And if you'll see, the monotonic is the right choice in every case. The multipool is the wrong choice in every case. And sometimes the multipool of mono can come close. But you're going to see this systematically throughout. You see there's an obvious right choice and an obvious wrong choice. And I argue that this is a broad enough example that if all of them agree, we don't need to look at more examples. We know. Okay? So just looking at what we measured here, the question marks means being investigated. So same with size variation. So the access locality is deliberately low. The memory utilization is complete. It's 100%. And there's no contention. So global allocators are consistently inferior when dealing with systems having short focus duration irrespective of contention C. For systems having utilization used such as those modeled in this benchmark, a monotonic allocator is always superior, especially when applied to static buffers residing in the program stack, similar to the effect of alloc and C. Now, alloc A and C. I want to tell you something. The person who actually did this benchmark did not do what I asked the person to do. Instead, created a static buffer of 1 billion bytes off the stack. And yet, you see the results. Imagine if the buffer had been on the stack, which is hot. These results would be only that much more outrageous. And good outrageous, not bad. So this is without the heat of the stack. Just saying. took that off the table. But with the stack, it would be only better. I just need to emphasize this is a lower bound on how good what we just talked about is. Do you have any questions? Yes.
Just a moment.
Would there ever be a case to use a global allocator at all? Or?
The question is, was there ever a case to use a global allocator? I would say 99% of the time use a global allocator. Because 99% of the time you don't care about performance. But that 1% of the time that you do care about performance, you really care about performance. And 100% of the time that you care about performance at all, think about allocators. How's that? And for those people that don't care about performance, that extra word in the thing isn't going to hurt you. I promise that. And in fact, you can't even measure it. It's that small. People get all worried about that extra word. It doesn't cause a problem at all. And compared to the value you get when you care about performance, it's like buying a $100 bill for a penny. Oh, you're getting 99.99% of the $100 bill for a penny. You don't want to buy it. No, it's too expensive. I can't do that. Whatever. All right. Long running. This is actually a hard thing to explain. I'm trying to debate whether I should explain it and try to finish on time or just go through it and let you ask me later. I'm going to do something in between. As I said, at the end of this, if you need to leave, leave. But I do want to finish what I'm saying, and the reason for that is for the video. So whoever's videoing this, you're on the hook for a couple extra minutes maybe. So what we're trying to do here is look at locality. Locality is the most important thing in any program. It totally dominates what's going on. We're going to simulate something that's a time-multiplexed system. And it's very much like how Bloomberg works. So we're talking about hours of access time and seconds of build-up and tear-down time. Here's a system. This is a simple model. I created a linked list of ints. So I've got a collection, a vector of linked list of ints. Looks like this. This is what Bloomberg does. We make billions of dollars off of a linked list of, a vector of linked list of ints. Pretty much, this is it. All right. So we're going to build this thing up. Rather, I'm just going to put this on the screen because trying to explain it on the screen. Basically what we're going to do, in a nutshell, without reading all the words, we're going to build up the system. We're then going to access the system with different access patterns. We're either going to access the system many times going through one list and then many times through the next and then many times through the next. And then we're going to do it half that many. So instead of, we're going to do this, then this, then this, and then come back this, till we go to this. That's what we're going to do. We're going to look at that different kind of access pattern. We're going to look at it for different size systems. So basically, we're going to build up the system. Here's a vector, and so what's going to happen? We're going to ignore the cache for now. So what happens? Look what's happening. We're adding individually. See what's happening? Now, true story, when I did this at my work, I had a computer that didn't have near the capacity that this one does. And so what happened is exactly the thing that I'm trying to show in the slide started to happen with the PowerPoint, and it slowed down, and it slowed down to the point where it was unusable. And I'm going to have to give that lecture again because I couldn't finish it. I couldn't even get the thing to work. It froze for exactly the reasons that I'm talking about right now. So what you get the idea. What's happening is as I go through, I'm allocating stuff from the global allocator, and because it's only one thing, it's coming right off the global allocator the way you'd expect it. So now what I'm going to do is visit each system in turn. And again, I'm going through this quickly because I have to. So let's see what this looks like. So here's the first subsystem, and I'm going to go and access each thing twice. Now, we don't know how long the list is, so this could take a long time. Okay, it's long enough. So anyway, it gets to the bottom, and now we've done a single iteration twice through of that. Now, we're going to repeat the sequence for a total of 2. Oops. I did that a little prematurely. There we go. So here we go. So what happens? So this is what it means to access a subsystem. The iteration count is 2. Then we're going to advance to the next subsystem. I did it again. Advance to the next subsystem. Okay. I have to remember where my pauses are in the talk. This is automatic. Oh, this is so much better than the other one. It was so painfully slow. Oh my God. This is a dream. Just imagine that this took 10 minutes. Okay. Okay. Now this is supposed to indicate that there could be a large number of subsystems, even though each subsystem is small. So this could take a long time. Okay, that's long enough. And then this happens. So remember, this is 2 iterations through each one. So that's what's happening. That consists of one axis of the system. But we're going to need to repeat this some number of times. So here we go, 2 to the 7th, some large number. Okay, and so and then we go through again. And again. You get the idea? Do I have to do all 127 times a large number? No? I still have to get my drink. Last time. I just want to make the point we're doing this a lot. So we're accessing it in this pattern. All right? So you get the idea. We're just going to do this. Then we're going to trade off between the number of times we go through the whole system and the number of times we hit each one consecutively. And that's going to change our locality, our temporal locality. It's not going to change our spatial locality at all, but it's going to change our temporal locality. The more times we go over something, the more temporal locality we get. If we go over it once, we minimize our temporal locality because all we got is our spatial locality. We got no temporal locality. Right? Maybe? When I say no, I don't really mean no because the cache lines give you a little bit of temporal locality in the sense that the next axis happens to be really close on the cache line. So remember, this is runtime. All right, so here's our pseudocode. Okay, so what we're going to do is we're going to ping the innermost element. That's that. And then we're going to do that each time through, so that's the number of subsystems. And then we're going to say the number of iterations, so we're going to do it twice. And then there are going to be some number of repetitions. Here we go, repetitions. Remember we did that 5 times before we got bored? So those are the parameters. You know what I is, you know what R is. And I times R is going to be a constant. So is the size of the subsystem times the number of subsystems. That's another constant. All right. So M and R are the constants. M and A, I mean M and A. So that's what we're saying. And again, I'm going through this quickly for people on the video so they can just look at it. But you get the idea. So n is equal to 45. That's 2 to the 45th. These things run a long time. If you try to do something 2 to the 45th times, it takes some time. Okay? We're going to do the cross product. So what does this say? Subsystem size, 2 to the 8th. 2 to the 3rd. And the number of subsystems, 2 to the 18th. Here we have the number of iterations is 2 to the 2nd, and the number of repetitions is 2 to the 22nd. So what does that look like? So here, 2 iterations, 128 repetitions. What does that look like? 4 iterations, 64 repetitions. What does this look like? 8 iterations, 32 repetitions. What does that look like? 8 subsystems, 256K. 16 subsystems, 128K. 32 subsystems, 64K. Okay? Now, those are some arbitrary numbers that I made up, but their relative sizes are important. Over here, we have high locality, and going that way, we have low locality. We'll see this. That's important. So if you look at this, when we start this thing off and we go through this process, you see how it's going through and it's filling things in as it does this is what the cache is actually doing. And it's going through, and it gets through a whole subsystem and goes to the next and goes to the next, but eventually it has to kick out the subsystem because it's too big. But it still gets through the whole subsystem twice. That's important. Whoops, I stopped it. I didn't mean to do that. What about diffusion? So what is diffusion? What do I mean by diffusion? So what I'm talking about by diffusion is as you do this stuff where you move stuff around in memory using a global allocator, what was really nice and packed and beautiful in memory when it came out of new starts to get scrambled like a washing machine. And so we're going to visit each subsystem, and we're going to pull something off, and we're going to put it somewhere else, and we're going to do this for long enough that the whole thing looks like it's been emulsified, like oil and water. It's going to become oily water. Okay? So what does that look like? So here, starting with this guy. So I just took that guy off. I deleted it. And now we have that. And now I'm going to new it. See, that's free now. Now I'm going to new it. And now it's over there. And what does that mean in memory? That means it's a different color. It's part of a different subsystem. It's the same physical location, but it's now part of a different subsystem. So I'm going to go through this process, and I want you to think different subsystem, right? So now I created a hole in this subsystem, in this region, and now I'm going to put it onto another subsystem. So now that piece is part of this subsystem, and I'm going to keep doing this. And you see what's happening? We're shuffling the memory. This is actually worth seeing. I want you to absorb this. People who tell you that moves are faster than copies are lying to you. They're lying. Depends on exactly what, but they're lying. They want you to think that. I don't know why, but it's not true. If you're considering access, don't move it. Because that's what we're doing. We're effectively moving these things, right? We're moving them so that relative to the subsystem, there's a piece of me that's somewhere else. My subsystem, I'm over there. I have to go here and there. My subsystem is distributed all over memory. What do you think happens when I go to access that subsystem now? Instead of having it all in cache at once, is it all in cache? No. So this is what happens when you do this stuff. You see what's happening? See how the memory is getting scrambled? And finally, this last guy. This took really like 20 minutes on the other. All right. And finally, we put this guy back and just try to understand what's going to happen here. That hole is going to get filled with the last one. So now what we did is we shuffled just one element from each list. Imagine I shuffle the whole list. What's going to happen, and if I had a really bad shuffle, say I used a bad random number generator, I get something like this. Why did I do this? Because I didn't have the patience to really put them in one at a time randomly, because I didn't want to go blind. But that's the idea. Now they're all different, and you won't get any goodness happen with your cache lines. All the goodness is gone. So your cache has now been rendered useless. This is called diffusion. Has anybody heard the term fragmentation? Does anybody know what it means? Sir?
When you have holes in your memory and you allocate a bigger block that doesn't fit in those.
Okay, he's absolutely right. So fragmentation is an antiquated term dealing with an antiquated process called coalescing allocators, where what they're doing is they're trying to keep the number of holes to a minimum. Now, obviously, the allocators today have to worry about holes, but they're also pooling allocators, like the multi-pool one. And so the small objects don't create holes. You don't just allocate all over creation. All the small things come from the pools, and so you have to worry about the big pieces. But what's happening here, this is not fragmentation. Look at this. This is packed to the max. But the memory from the different subsystems has diffused throughout the memory that you're using. So if somebody says, oh, the memory is fragmented, you say, I'm sorry, but it isn't. It's diffused. Okay? You heard it here first. If you didn't, tell me who told you that before. This is fragmentation. And this is what happened with coalescing allocators, where they just got it from anywhere and then they had to worry about it. This is really bad fragmentation. This is not what's happening. I just want to make it clear. If somebody says fragmentation, yeah. Okay. So, this is what's happening here. Every time we go to access things, before we even get through one iteration, We're already pushing stuff. Now, that's one complete iteration through one subsystem, but we've already lost all our data. So you see what I'm saying? It's really important that we not have the diffusion because we get no benefit from our cache anymore. Right? I hope you understand. That's a big deal. So overall plan, we're going to create an access after the shuffle. We're going to create an access before the shuffle. We're going to create only the shuffle. We're going to measure the wall time, and we're going to look at the ratio of after minus the construction time, and we're going to divide that by and before the construction time. So let me get that. So after is a bigger number divided by before, which is the baseline. So before the diffusion, we have the baseline, and after is what happens when the programs run for a long time. And that ratio is important, except the cost of setup is negligible, so forget it. So it's just after divided by before. Although what you're going to see actually takes it into account. It's 0.00. We'll call that the degradation ratio. So we're dividing create shuffle access divided by create access shuffle. Does that make sense? This needs to make sense. You're looking at the time when the system starts up. You're looking at the time after it's been running for a day. You're going to divide the startup, the after a day time by the startup time and see what the degradation ratio is after a day. How much worse is it after a day? Okay? All right. So here's a nice little heat map of, and this is the first measure I did, and I did it in powers of 10, and I regret it, but I didn't have the patience to go back and do it, so tolerate me. It actually makes a good point. When you have subsystems of size 10 to the 6, and you have 10 of them, you notice that, wow, shuffling this stuff really matters. Just look at that. So this is iterations per subsystem. This is diffusion. This is if I shuffle once, like 0 times, I'm sorry. This is if the subsystem size is the same as the overall. Then all I'm doing is just rotating a list and there's no effect. So you know that at the edge cases, where I'm either not doing anything or not shuffling at all, it has the right numbers. Now you can see if I shuffle once, I get some serious factor degradation. You know, look at the difference as you go through. The degradation eventually stabilizes, saturates, and we're going to use 5 for the rest of this talk. Notice that when I have 10 subsystems of size 10 to the 6th, it sucks. That's a technical term. It really sucks. All right? So look at that number. That is an order of magnitude, legit order of magnitude. Okay? This is not a, I mean, seriously. That is important. If anybody doesn't care about a factor of 15.6 over time, you should have been to my previous presentation because that was about how slow it went. Okay, do you have any questions about that? Okay. So let's look at some stuff. So let's look at this thing. Remember this thing? Now we're going to look at what we call a three-dimensional heat map. So this is a picture, and the red stuff is the stuff that takes a long time. And that circled 15 number, remember that? That's a big number. Now what is this? This is as I'm going through the thing here, the locality is very high. That means I'm going through 256 times before I go to the next system. The 128, 64, 30, all the way up to here, which is I'm going through the thing one time. So locality, temporal locality is that way. Here, it's the whole system is one system all the way down to each subsystem is one element. And so the physical locality is getting bigger as the size, my subsystem size goes down. Something crazy happens over here when I have a subsystem of size one element and I go over it only twice. This thing just blows up. I don't know what that is, but it's reproducible. But I don't care because that's not a data point that anybody cares about. What we care about is the stuff in the middle of the thing where you have real subsystems of a few bytes and a few, and you iterate over them more than one time before you go somewhere else, because otherwise it's all nonsense. All right, so now this is without local allocators, okay? And that's the max temporal locality. I'm just showing you that. That's the subsystem size. This is an anomaly. This is where we should be very concerned. When we go from the maximum size down one order of magnitude to 10 subsystems of a tenth the size of what we're doing, we get some real problems. We also get some real problems when our temporal locality, that's physical, that's the physical locality, This is temporal locality. When the temporal locality gets really low, then we really need to start thinking about doing something, okay? Look at that number. Now, this is my magic. I'm going to transform this into a spreadsheet by continuously deforming this. How many people have studied complex analysis? This is called a continuous deformation. We're not going to go around a singularity. Watch. Yay! Okay. So if you look at this, there's some interesting stuff. Down here in the normal region, this is in the valley. Yeah, it's no big deal. Factor of 2, factor of 4, not a problem. But when you get to the edges, and we can get to the edges, it can be a big problem. So those are smaller subsystems. Subsystems reaccess more frequently as we go this way. These are smaller subsystems. So you understand, this is better physical locality, this is better temporal locality. But as soon as we lose temporal or physical locality to a point, we get some serious degradation. Again, if you have only one system and a global allocator, even a local allocator won't help you, because if the local allocator refers to all of the memory in your system, it's not partitioning anything. Now, this is the anomaly. If I erase it, if I gray it out, it doesn't change this particular data set. So there's my 18. 18 is the magic number. 2 to the 18th, there's something in my machine at 2 to the 18th that's crazy. I don't know what it is. Now let's introduce a local arena. The whole thing, every one of these subsystems has a local allocator. This is not a thread local allocator. This is a time multiplexed local allocator, because we as engineers know what our subsystems are because they're objects, hopefully. And so we put in the object a local allocator, like I did there, right? And then what happens? We box up that memory that we allocated from new into its own little container. And which local allocation strategy would you use here? Does anybody have an idea? We saw in the previous one, we'd love to use the monotonic allocator, right? But here, maybe not, because we're allocating, no, we're not counting the shuffle, or are we? Because at some point the shuffle stops and now we're just accessing. What will we use? It turns out it doesn't matter what we use, but if we were going to use anything, let's just use the multipool allocator backed by the monotonic. That would probably be the one I would use. Any of these would work. And we don't really care. It has low utilization due to the shuffle, but without the shuffle, it has high utilization. The thing here is any allocator at all, any local allocator would be good. Anything. I mean, anything. Now, this is the same thing with a local allocator. You notice before it was like 15, and now it's 2.5? So if you take the ratio of the two, this is what we're talking about here. This is without to with. Now what we're talking about is how bad was it before, how, divided by how good it is now. And you see that there's a factor of 20-ish. It's on that scale. The improvement can be as high as that much. I just want to emphasize, look at that. It's not quite 20. Over here it is, but this doesn't count. But you could still see it's significant. If I take that away, again, an order of magnitude for sure. That's 10 times better with the allocator than without in that particular point. And there are some other places where it's even a little bit better. This is for a system of size 2 to the 21. We can repeat the experiment with 2 to the 25, so we see something even bigger. When things get bigger, this becomes more pronounced. So I'm going to just show you the same thing you just saw. We're going to wink that out. And so this is without local allocators. 18 is still the number. Notice things get bigger, but still at 18, something magical happens. It's a property of the machine. Look, this is with local allocators. We're still doing better. And without, we have this. So now I'll wink that out. 18 is still the magic number. And we see things like a factor of 16 speed up in places. But even if you don't care about that, what if it's just in a not so good, and all it is a factor of 3? A factor of 3 is nothing on a long-running system. I mean, where here wouldn't you take this? You want, 22% speed up? No? So you have to decide, but I think this pretty much speaks for itself. So allocation density is nil, chunk size variation is nil, access locality is what we're measuring, utilization is 1 except for the shuffle, and allocator contention, 0. Takeaways: for long-running systems, the speed of allocation, deallocation operations themselves may be entirely irrelevant to overall time performance. Partitioning memory corresponding to subsystems having physical and temporal locality can nonetheless make an enormous difference in overall runtime performance. Does anybody believe that there might be some runtime performance benefits for allocators at this point? Because if you don't believe it now, I give up. Okay, I'm going to just race through the last one for completeness. There are 2 more. The short running one, this isn't exciting because this is just showing you where allocators can go bad on you. So this is just an example of a pump. And it's better to just show you the pump. So here's the pump. I'm going to load up something. Here I'm loading it. And then I'm going to go through the process of just deleting one, allocating one, deleting one, allocating one, deleting one, allocating one, deleting one, allocating one, until I've done it a whole bunch of times. And then what am I going to do? I'm going to get rid of it. That's all I'm going to do. That's the experiment. And so, this is runtimes. So, I'm putting this up there for everybody to take a look. But here's the idea. We're going to use, here we go. Yeah, you want to look out for the monotonic allocator because at 2 to the 12th, it has this implementation detail that it passes through. And so remember that anything that it passes through is going to be oversized, and so it's going to go straight through. So 2 to the 12th is a magic number for the monotonic. Okay. These are all powers of 2. The total amount of allocated memory is 2 to the 30. So that's total. And then you see that these are M is the maximum active memory, and S is the size of each chunk. And so now and these are all in absolute times. Excuse me, not all. These are all in absolute times, and these are relative percentages. Okay? So having seen that, take a look at the bottom here. These are all things that are above 2 to the 12th. That's why the brackets are there. So you can watch out for what happens. Notice the red things, see? Oh, look what happened. So when the memory got too big, the monotonic allocator, because of the pass-through, just ran out of memory. Okay? And you see this failed too because it's a pass-through, and the pass-through, right? Because it's backed by it eventually went, yeah, you know what I'm saying. It went through the multipool to the mono, and so that's the failure here. Here, it's able to return it, but as soon as it goes above 2 to the 12th, then it goes to the mono, and the mono can't return it, the monotonic one. So that's what's happening there. So I just want you to see, if you're not careful, you can get into trouble. So the allocation density is high, variation is 0, access locality is low, utilization is being tested, but it's relatively low because we just have a small thing and then we're just allocating a lot. And the allocator contention is 0. Never use a monotonic allocator by itself when the utilization U is low and the total number of bytes allocated is large, e.g. in a loop. You've been warned. Beware that a multipool passes through its request to the backing allocator when a chunk of size of memory being allocated exceeds some maximum pool size, and in this implementation is 2048. Okay? This is here basically just to show you that you can't shoot yourself in the foot or worse. All right, questions? Okay. So this is the contention one. This is a completely canned check mark. We're not trying to prove how much better local allocators are. We already know they're much better. We just want to show you that without trying, giving full deference to the mechanical ones that try to pretend that they can compete, that we destroy them without even trying. So that's all this is. We're just going to do the standard thing. We're going to create a bunch of threads. We're going to have local allocators and not local allocators, basically. I'm putting this up for people to see, but it's not important because I'm telling you, we didn't try to do this. It just fell right out. High density, I'm putting it up because you know what? This is not a legitimate experiment. If we wanted to completely destroy those things, we could completely destroy them, but we're not going to. We're just going to lightly destroy them. So take a look at these numbers. It doesn't even matter what the numbers are. If you just look at them, here's absolute times for the default, and here's the virtual one. Notice here, the worst thing is this guy. These guys with virtual, but this is percentage of this, and this is the default allocator. So this 91 means that it's, with the virtual function, it's faster than it is when it's defaulted by the compiler. Okay, so I'm just going through this. Number of active threads, and here we go. We're going to change some things. Look at the monotonic. This is a poor choice because what's happening is the utilization is going to wind up being high, I think. So we're going to see things get worse. And again, the point is, whoops, let me just go back. The point of this is single-threaded, this is multi-threaded. At the end of the day, don't use a monotonic, use the general purpose local allocator, and these numbers, basically it's 4 to 5 times faster to use a local allocator in a threaded application. If you give the deference to the general allocator, now if you try to beat it for real, if you really try to set up a benchmark where you have an advantage over it, where it doesn't know about thread affinity, so it's going to make the wrong guesses and all of that, it's so not fair. It's so ridiculous. But I think a factor of 4 or 5 is enough to make the point. So we didn't spend any more money on it because we're just going to do it. Up to you guys. All right. So again, density is high, variation is 0, access locality is low, memory utilization is nil, and it's either 0, which is the single-threaded one, or high. So the takeaway is make subsystems memory explicit using local allocators to obviate affinity in thread pools, as well as thread-aware global memory allocators. Use a composite multi-mono allocation strategy. Those guys, when utilization U is low, especially when variation V is high, so long as the size of the individual chunks are smaller than the pooling threshold 2K. This isn't everything you need to know about allocators. What do you need to know about allocators? Is that you need to know about allocators. That's it. Any questions? How am I doing? All right. I'm going to just finish this because I'm actually really close to finishing this, so I'm going to actually finish this. I want to mention fault sharing. How many people know about fault sharing? Who feels brave enough to tell me what fault sharing is? Okay.
Fault sharing is when you access the same cache line or the same memory, which is accessed by 2 threads at the same time, and therefore it's always getting the cache line, and therefore.
So let me ask you, can you see how allocators could possibly, I'm just going to repeat, so when 2 different threads are accessing data that's unrelated but happens to reside on the same cache line, we call that fault sharing. Can you think of how allocators might prevent that?
Yes.
What do you leave new data on the new cache?
If every thread has its own allocator in a separate region of memory, we would have no fault sharing. Just saying. Okay. Not that anybody cares about that stuff, but I just thought I'd throw it out there. Okay. There was a problem in the original experiment. It's really stupid. We had all the right data, but we screwed up a script that had reversed the first block of 4 numbers with the second block of 4 numbers, so it looked like the multi-pool allocator was behaving like the monotonic and vice versa, which made absolutely no sense. And there was some suggestion we should try to explain that. And on the first, the paper had to go to the standards committee because it was for the standards committee, and basically said, no, we're not going to explain it because it's inexplicable in terms of data. We'll present the data because we did take the data, and we'll figure it out. So eventually what happened was, well, I'm getting ahead of the story a little bit, but we needed to figure out what was wrong. So this is what happened. So there's this guy named Graham Blaney, and he's the best co-op student anyone's ever had. And he worked at Bloomberg, and he has absolutely defied any kind of expectation. And I said, you know, when he was done, I said, hey, Graham, would you mind just repeating the experiment that we did? Oh, and by the way, don't look at any of the code. I'll explain to you what we did. Can you just do it from your head? Yeah. Okay, so he talked to the people. He went and did it. Got the same numbers, but oops, the columns were reversed because the script that took them from the data and put them into the table was reversed. So we got the confirmation of the data, and we found the bug in our script. So we got the same data and we found our bug, and now we know from a completely independent source that the data is reproducible from verbal description, not even reusing the code, not reusing anything but verbal description, what I just told you right now. You can take this slide and you can go recreate what I did and you'll see the same effects because we know, because we've done it. So that's what happened here. And now we have something called fragmentability. Now, I didn't word this. This is Graham. And remember, he wasn't even out of school when he came up with all this and presented at the committee and convinced them to adopt polymorphic memory resources. But this is what he said. A measure of potential of subsystems allocated memory to become diffused throughout physical memory as a result of the interference of some subsystems memory allocation. If a subsystem is fragmentable, i.e. other systems are present in the process and the subsystem allocates more than one chunk of memory, F is greater than 0. I didn't help him with this. He came up with this himself. This guy isn't even out of school. He didn't want to work at Bloomberg because Bloomberg doesn't have enough to challenge him. So I gave him this. He got the stuff accepted to the standard along with the other two concrete allocators, and I finally convinced him to join. Whew. And we're very lucky. No, you can't have him. He's ours. All right, so this is low fragmentability. This is medium, low. This is medium, high. And this is high. And what's nice about the fragmentability thing is that you can look at a data structure and say, how badly does that thing want an allocator? If it's a vector of int that you've sized up front, nah, it's not going to do you anything. And then if it's a map of maps of little stinky things that have lots of little bits and pieces, yeah, you want an allocator. Okay, so he did a really good service there. And this darn thing was accepted on March 5th. And he talked, by the way, 2 days earlier, and he convinced the standards committee to do this, I swear. It wasn't just me. I needed the independent confirmation. So he did it. He spoke. It was quite something. Here are some references, just so you know. And his, Graham Blaney, is on the list of references. And now some conclusions. Are memory allocators worth it? What do you think? Maybe? I'm going to say yes. There are quite a few reasons why I might want to use it. So to improve performance, and here are just some examples, but also to place things in different kinds of memory. So when I need to put something somewhere, that's what you use an allocator for. And to measure, test, and control. And it's remarkable how much control you can get because you can give a subsystem a memory allocator that can actually measure what this object, not what the system as a whole does, but what this object, this instance of a subsystem is using. I cannot tell you how valuable that is, but I will tell you that managers that are 2 levels up from me think that's more valuable than performance. Okay. So, suppose you have a program that's large, long-running. Subsystems are accessed disproportionately often. So, in the case where neither of those is true, it's small, and subsystems are accessed evenly, use a global allocator, right? Now, if they're large and there's uneven access, in other words, here, then here, then here, then here, use a local allocator. If it's a small system, you might still want to use a local allocator. Here's the problem. If you have a huge system and memory is just by design or whatever, or lack of design, accessed all over the place, and a local allocator can't help you, what do you do? I am not kidding. All right. Same kind of thing, but this time the subsystem exhibits high memory utilization. If it's a small program, use a global allocator. If it's a large program and it does have high utilization, use a monotonic allocator. If it's a small program and it has high utilization, maybe you want to use a monotonic allocator. But if it's a large program, meaning it's doing a lot of stuff, and it doesn't have a high utilization, what do you use? You use a local multi-pool allocator because it gives you the locality, doesn't pay for all that extra stuff such as synchronization, and it could be a single-threaded program, but it still gives you what you need. It's not going to break because it gives the memory back. Make sense? Okay. Next one. Program's large, long-running, subsystems run concurrently. If it's a small program, use a global allocator. It's no big deal. If it's a large program and subsystems run concurrently, use local allocators, obviously. If it's not a large program, you might want to use local allocators. And if it is a large program, but there is no concurrency, what do? You use local allocators. Okay. The performance impact can be substantial. Okay, in every benchmark, use of some, if not all, of the local allocators perform no worse and typically much better than the default allocator. That's a fact. We didn't hide any data. We didn't cherry pick. We created 4 benchmarks. We picked data that was representative, and there is no case where the global allocator won. That's got to be worth something. For long-running program, improvements of as much as an order of magnitude were observed. The overhead of using virtual functions, function interface, in the default case, holding an extra address was minimal to non-existent. So let me say that again. The overhead of using a virtual function interface is effectively 0 in and of itself, and compared with the benefit that you get, OMG. And for people who don't care about allocators and have to pay some infinitesimal overhead in parts of the program that make no difference, they won't notice. They couldn't. They'd have to instrument their code down to the nanosecond to be able to measure any overhead at all if it exists. It's not clear that it does. So, object-level control over memory allocators is intrinsic to C++ and must always be so if we hope to maintain the language's supremacy as the best-performing high-level systems language. Supporting object memory allocation is admittedly an added burden, exacerbated by an initially difficult-to-use model, which is finally being addressed in C++ 17 by polymorphic memory resources. I want to reiterate that C++ 17 is a breath of fresh air because it's a whole lot like what I invented in 1997 that was trivial. It was so easy back in 1997, and finally, with great minds, we've been able to cram something that is so simple back into such a complex language. But there's even better news. We're working on something where we're going to take allocators entirely out of the language. Here, any future incarnation of SDL should incorporate the lessons elucidated here, but we're going to let the compiler do it for us. So all we need to do is have Siri for our compiler and say, Siri, make this allocator aware. Yes, sir. And that's it. There's no interface. It's just now, you just said, make it allocator aware. It's allocator aware. And then you say, inject allocator, and it goes, yes, sir. That's it. You don't have to know about it. It's just like a VTab. You don't need to know about it. It's there. You don't need to know. And the compiler can do a better job than a human because the compiler has access to everything and never makes a mistake, and there's no maintenance overhead, there's no runtime overhead, and there's tremendous benefit for improving performance and everything else. So I just want to remind you of our acronym, DivLoc, and then there's fragmentability. So everybody say F DivLoc. But don't mess with the duck. All right, that's it.